Hi guys! In this video, we will thoroughly discuss the nomenclature of organometallic compounds, and this video will focus on the transition metals, or the metals that is under the D block of the periodic table. Our discussion will be based on the following. First, the nomenclature of organometallic compounds of the transition elements, IUPAC 1999 Recommendations, as well as Nomenclature of Inorganic Chemistry, IUPAC 2005 Recommendations. This is frequently referred to as the Red Book. So the objective here is to integrate the classical inorganic coordination nomenclature as well as the organic substitutive naming conventions. So our assumption here is that you can name various organic compounds like alkanes, alkenes, alkynes, and aromatic compounds since they will act as ligands in your organometallic compounds. This will be the contents of this video. First, we define what organometallic compounds are, and then we will recall the rules on writing coordination formula and writing coordination name. And then we will proceed with naming organometallic compounds with different cases. We have one metal-carbon bond, compounds with multiple metal-carbon single bonds, and then we have chelating ligands which use the Kappa convention. We have bridging ligands which use mu notation, and then we have multiple metal-carbon bonds, and we have haptic ligands which use the eta notation, and finally we have organometallic compounds with metal-metal bonds. By definition, an organometallic compound is a species which has direct bond, coordinate covalent bond, or dative bond between a carbon atom of an organic molecule and a metal atom. And since it contains a metal and an organic ligand, naming the organic substituent must be consistent and coherent with the organic nomenclature that we know in your org chem classes. So here are some examples of organometallic compounds. Here we have Zeiss salt, or potassium trichlorido eta-2-ethene platinate -1, which is the very first transition metal organometallic complex that is synthesized. Notice that we have the eta notation, and both carbon atoms on the ethylene are bonded to platinum. So in the later section, we will discuss that on how to use the eta notation. So next, we have ferrocene. This is a sandwich complex, and it is like a sandwich since you have two planar rings sitting on top and bottom of the metal center. So throughout our discussion, our goal is to systematically name this type of complexes. Before we deal with organic ligands, let's review the nomenclature of coordination compounds. Whenever we write the formula of a coordination entity, the metal center must always be listed first. Following the metal, we list the ligands, anionic ligands first in alphabetical order based on their formula, and then followed by neutral ligands. Also, the entire coordination sphere, whether the complex is charged or not, we must enclose it within the square bracket to indicate that it is a coordination entity. If your ligand is polyatomic, or if its abbreviation is used, we must enclose them in parentheses. And lastly, when nested brackets are required, we alternate the use of parentheses and braces since we enclose the whole thing in square brackets. Okay, so now let's look at the following examples. So in this complex, tetraamine chlorido nitrito cobalt, anionic ligands are written first. That's why Cl followed by NO2, and then we write the neutral ligands. So it is followed by amine. Next, for tris-ethylene diamine cobalt 3 chloride, En there is ethylene diamine. The abbreviation must be enclosed in parentheses. And lastly, in this iridium complex, chlorido and hydrido, these are your anionic ligands. That's why they are written first. followed by carbonyl and 2 molecules of trimethylphosphane. So with the trimethylphosphane ligand, it is properly parenthesized. Since we have the parenthesis for methyl groups, we will use braces to enclose the whole p-meth3 ligand. When converting a formula into coordination name, the order will be inverted. We list first the ligands alphabetically, regardless of charge, and then it's followed by the metal atom. Also, numerical prefixes such as di, tri, or tetra, they are completely ignored during alphabetization, and only the initial letter of the actual ligand name is considered. For ionic complexes, we name the cation first and then the anion. And if the entire coordination entity carries a net negative charge, the name of the central metal must be modified to have an ending 8. And the net ionic charge is then appended in parentheses. Lastly, for nesting, it will be an alternating parenthesis, square bracket, and curly bracket. Okay, so now let's consider the following examples. So for this complex K2PDCl4, we have the cation potassium, and the name of the anion is tetrachloropalladate. So in this example, the complex coordination entity is an anion. So palladium now becomes palladate. And don't forget to write the charge of the whole complex, which is -2. Next, for this cobalt complex, we have chlorine, nitro, and amine as ligand. So the whole name will be tetraamine, chlorido, nitrito, and cobalt 0 if we alphabetize the ligands. So for this cobalt complex, I want to emphasize that only in writing formula, we will list the anionic ligands first. But when you write the name, we will list all ligands alphabetically, regardless even if it's anionic or neutral. So for this complex, actually it is quite big and it's hard to name. So this is the name of this complex, and we will just use this complex to focus on the nesting order. So for our nesting order, so for example, in diphenylphosphanyl, we already used the parenthesis. That's why for the bis diphenylphosphanyl methyl, so since it is bigger, we will enclose it in square bracket, and followed by, if we are pertaining to the whole bis mu3 bis diphenylphosphanyl methyl and so on, it is enclosed by the curly bracket. Now let's proceed with ligand names. For classical inorganic anions, our rule is that we replace the ending "ide", "ate", or "ate" of the anion by "ido", "ito", and "ato" respectively. So when we look at this table, for example, chloride becomes chlorido, acetate becomes acetato, and so on. For neutral components, the most common names are preserved with specific exceptions. For example, amine or aqua for water. And actually, we can also treat organic compounds as anionic ligands. So we can name them as anionic ligands. Actually, they are derived from sodium or potassium salts, like sodium acetylide or sodium methanide. So for this, our rule is we drop the terminal E and append "ide" before converting to "ido". So for example, a methane-derived ligand becomes methanido, and cyclopentadienyl becomes cyclopentadienido. And for this type of naming, the atom with the free valence is given a number as low as possible and must be consistent with the established numbering of the parent hydride. So the locant number, including 1, must always be cited. So for example, in prop2N1 ido, the locant 1 is still placed and it means that the carbon number 1 is deprotonated and bears the -1 charge. We can also treat organic ligands as radical substituents. So letter A, if you have saturated acyclic and monocyclic hydrocarbons, here we simply replace the parent -ane suffix with -il, and under this specific method, the radical carbon atom with the free valence is implicitly defined as position 1, meaning we omit the locant number from the final name. So for example, we have methyl, ethyl, or allyl. We do not place locant number 1. However, for longer or branch chains where ambiguity can arise, we use the general method. So for letter B, it appends -il to the parent hydride name after removing the terminal E, but it requires that free valence locant must always be cited even if it's 1. So this gives rise to highly precise terms like pentan 1-il or cyclohexane 1-il. We will always place the locant 1. For pentan 2-il, this means that pentanyl will attach to the metal center through carbon 2. When dealing with heterocyclic systems or fused polycyclic hydrocarbons, we will follow the standard IUPAC nomenclature for organic compounds. So the locant, indicating where the metal-carbon bond is, it must be placed directly before the -il suffix. So let's consider the following examples. For naphthalene, this is a fused bicyclic system with the following numbering. That's why, as a ligand, if this is the attachment to the metal center, it will be named as naphthalene 2-il, since it will be bonded to the metal center through carbon number 2 or the beta position. So next example, let's consider this morpholine ring. This is a 6-membered heterocyclic ring containing oxygen and nitrogen in the ring. And as we can see in the numbering, oxygen takes position number 1 even though it's not a carbon atom. So numbering around the ring places the radical carbon adjacent to the oxygen. So the name of the ligand will be morpholine 2-il. So if as a ligand, the name will be morpholine 2-il. Aside from this, I want you to recall on how to name bicycloalkanes and spiralkanes. Let's have some examples for naming organometallic compounds with one metal carbon bond. So first, we have this osmium complex. As we can see, it has 5 neutral amine ligands, so that will be named as pentaamine. And we have 1 ethyl group. So if we adopt the anionic ligand naming, C2H5 came from the protonated ethane called ethanide. So the anionic ligand name is ethanido. So the complex name will be pentaamine, ethanido, osmium 1 plus chloride. Next, if we choose the radical substituent naming, we will name C2H5 as ethyl. So it becomes pentaamine, ethyl, osmium 1 plus chloride. Next example, consider this platinum complex. Here we have acetyl group, a methyl group, and 2 of triethyl phosphane ligands. So if we use the anionic system, the acetyl group can also be named as 1-oxoethane. That's why it becomes 1-oxoethan 1-ido ligand if it is an anionic ligand. And also methyl becomes methanido. So the name will be methanido 1-oxoethan 1-ido bis triethyl phosphane platinum. So if we arrange them alphabetically. Next, if as substituent, we list the ligands alphabetically. So acetyl becomes first, followed by methyl, and then triethyl phosphane. So the name is acetyl methyl bis triethyl phosphane platinum. And since acetyl can also be named as 1-oxoethan 1-il, we can also name the complex as methyl 1-oxoethan 1-il bis triethyl phosphane platinum. So it follows the proper alphabetization. Moving on to the next scenario, When a single organic ligand forms more than one metal-carbon single bond, it acts as a chelating group, or it forms chelate rings with your metal center. So to name these species, we append the suffixes diil or triil for the substituent method, and we use diido or triido for the anionic ligand naming. So we add this to the parent hydrocarbon chain. And just like in the previous section, we cite the locants using the lowest possible numbering system. So for example, a straight 3-carbon chain is called propane, and since we remove one hydrogen to carbon 1 and one hydrogen to carbon 3, our ligand becomes propane 1,3-diil if it's substitutive name, and propane 1,3-diido if you have an ionic ligand name. Same with butane, we have butane 1,4-diil or butane 1,4-diido as a chelating ligand. Now let's name these organometallic complexes with hydrocarbons as chelate rings. So example 1, in the platinum complex, we have 2 PPH3 ligand, so that's bis triphenylphosphine. And as we discussed previously, butane will be named as butane 1,4-diil if it acts as a chelate ring. So the systematic name will be butane 1,4-diil bis triphenylphosphane platinum. So starting from this part, I will use substitutive naming since it's easier. And next example, we have iridium complex with 3 p-3 ligands, so that's tris triethylphosphane. And we have unsaturated chain with substituents. So as we can see, we have 5 carbon chains, and double bond or alkene is at positions 1 and 3. So we also have methyl groups at carbons 2 and 4. And the attachment to the metal is through carbons 1 and 5. That's why our ending should be 1,5-diil. So naming this diene, it will be 2,4-dimethyl penta 1,3-diene and 1,5-diil in the ending. So the name of the complex will be 2,4-dimethyl penta 1,3-diene 1,5-diil tris triethylphosphane iridium plus 1. To avoid ambiguity, when ligands have multiple potential donor atoms, we use Kappa. So the Greek letter Kappa, it identifies which specific donor atoms are attached to the metal. To use Kappa, we need to differentiate identical elements using primes or ligand locant numbers. So for example, if we have a ligand where attachment is at nitrogen atom at position 1, and this is an unsymmetrical heterocyclic ring, we write it as kappa n superscript 1. So this eliminates any confusion if there are other nitrogen atoms present in the ring. So we can also denote multiplicity using the superscript. So for example, if we have acetate ligand coordinating to the metal center through the 2 oxygen atoms, we write kappa squared acetate. So this tells us that 2 structurally identical oxygen atoms are bonded to the metal center. For aromatic organic compounds, we can omit writing kappa C, but sometimes it is placed for clarity. So for example, let's have this complex. So aside from the organic ligand, in this rhodium complex, we have chlorido and hydrido, as well as 2 moles of triisopropyl phosphane. So that's bis triisopropyl phosphane. For the organic ligand, instead of naming it as a ketone, so we have 1, 2, 3, 4. So instead of naming as butanone, we treat the C double bond O as substituent or as oxo group in carbon 3. So we can place kappa O in the name. And we also have methyl group at carbon 2. So our name will be 2-methyl 3-oxo but 1-ene. So we have butene here. And lastly, the metal is coordinated to the ligand through carbon 1. So we will place 1-yle at the end. So the complete name of the ligand is 2-methyl-3-oxo-kappa-O, but 1-N-1-yle. And the complete name of the complex will be chlorido-hydrido 2-methyl-3-oxo-kappa-O, but 1-N-1-yle, bis triisopropyl phosphane rhodium. So next example, for this nickel complex, the metal is coordinated at ortho position of one phenyl ring in the PPH3. So the phosphorus atom also binds to nickel, which we denote as Kappa P. So if we shift our focus to this phenyl ring, we have phenyl Kappa C1, and at position 2 we have a substituent where we can call as diphenyl phosphanyl, and if we append Kappa P, that's diphenyl phosphanyl Kappa P, to indicate that it's bonded through the phosphorus atom. So the complete name of the ligand will be 2-diphenyl phosphanyl Kappa P, phenyl Kappa C1. So Kappa C1 here is added for clarity, but we can also omit this Kappa C1. And for other ligands present, we have hydrido and triphenyl phosphane. So the complete name of the complex is 2-diphenyl phosphanyl Kappa P, phenyl Kappa C1, hydrido, triphenyl phosphane, nickel. So in here, we can also observe the structures that we have arrows pointing to the metal. So arrows can be used to indicate a coordinate dative bond. While if we have straight line, like in here, it is used to indicate in covalent bonding. The Kappa convention is also used for resolving ambidentate ligands. So recall, ambidentate ligands are monodentate ligands that possess more than one potential donor atom, but it can only coordinate only one at a time. So an example is nitrito ligand. So if the ligand coordinates through its nitrogen atom, we place kappa directly after the ligand name. So the name is pentachlorido nitrito kappa N cobaltate 3-, since it is attached through nitrogen atom. But if the ligand binds through the oxygen atom, we will write nitrito kappa O instead. So this notation eliminates the older ambiguous terms nitro and nitrito, since in older nomenclature, we use nitro if it's bonded to N, while nitrito if it's bonded to O. So the same will be the case for thiocyanate ligand. We can use thiocyanato kappa S if it's bonded through sulfur, while thiocyanato kappa N if it's bonded through nitrogen atom. Next, when a ligand bridges two or more metal centers, we use the Greek letter mu. So the symbol mu is placed directly before the ligand name, and it's separated by a hyphen. If the ligand bridges exactly two metals, the N or index is equal to 2, and we omit the subscript. However, if it coordinates three or more metal centers, we must explicitly state the bridging index. So mu3, mu4, and so on. So for example, a single methyl group bridging two metals is simply mu-methyl, but if it connects three metals, it will become mu3-methyl. So a bridging ligand, CH2, is named mu-methylene, while if methane is deprotonated 3 times and the carbon bridges 3 metals, it's called mu-3-methane triyl. So other examples, we place mu to ethane 1,2-diyl if it's a bridging ligand. So the bridging ligand name will be mu-ethane 1,2-diyl, and here we have mu-ethane 1,2-diyl. In naming complexes with bridging ligands are alphabetized first before placing the terminal ligands. And if an identical ligand exists in both bridging and terminal modes, the bridging mode is cited first. So let's look at the following examples. Number 1, for this complex, we have two metal centers with the same terminal ligands. We have 4 amine ligands, each cobalt center. So we can name it as bis tetraamine cobalt. And if we have amido and hydroxo as bridging ligands, we have to append mu. So to name the complex, we write the bridging ligands first alphabetically. So that's mu amido, mu hydroxo, and followed by bis tetraamine cobalt 4+, the charge of the whole complex. Next example, we have two iron centers with two bridging carbonyl groups, and for each iron, we have a terminal carbonyl and one C5H5 or cyclopentadienyl ring. So the bridging carbonyls are named first as di-mu-carbonyl and combined with the identical two iron metal centers with the same terminal ligand, the complete name will be di-mu-carbonyl bis carbonyl cyclopentadienyl iron. If a ligand forms metal-carbon multiple bonds, the ending is ylidine for metal-carbon double bond and ylidine for metal-carbon triple bonds. So we have the following rules. Letter A, for saturated acyclic or monocyclic groups, we replace the ane ending of the parent hydride. So the carbene or carbine carbon is implicitly at position 1 and the locant is omitted, giving us, so for example, in here, propylidine. But for the general method, the suffix is appended directly after dropping the terminal E, and the locant one must be explicitly stated to maintain clarity. So for example, if propane is bonded to metal through carbon 2 and it is a metal-carbon double bond, the ligand name will be propan-2-ylidine. So another example, in this case, the propane is bonded to two metals, both through carbon 1. So one metal-carbon bond is a single bond and the other one is a double bond. So we name it as propan-1-yl, 1-ylidine. So here are other examples for cyclic hydrocarbons with metal-carbon double bonds. So for example, cyclopropylidine, if it's cyclopropane and the bonding to the metal is a double bond. The same with cyclobutylidine and cyclopenta-2,4-diene-1-ylidine. So next, we have triple bonds. We have methylidine, ethylidine, propylidine. Okay, so let's apply the rules for the following organometallic complexes. So these complexes will involve multiple metal carbon bonds. First, for this chromium complex, we have 4 carbonyl groups, 1 iodide or 1 iodido, and this organic substituent with triple bond to the metal. So looking at this organic substituent, if we treat NET2 as a substituent to methane, that will be diethylamino. And since we have triple bond for the metal and carbon, the name will be diethylamino methylidine. And the complete name of the complex will be, since we have 4 carbonyls, tetracarbonyl diethylamino methylidine iodidochromium. Next example, for this iridium complex, we have 3 triethyl phosphane ligands. And this hydrocarbon with metal carbon single bond at carbon 1 and metal carbon double bond at carbon 5. So the ending should be 1-yl 5-ylidine. And to name the organic compound, we have carbon-carbon double bonds at starting at carbon 1 and at carbon 3. And at carbon 2 and 4, we have methyl groups. So the complete name of the ligand is 2,4-dimethyl penta 1,3-dien 1-yl 5-ylidine. And for the whole complex, it will be 2,4-dimethyl penta 1,3-dien 1-yl 5-ylidine tris triethylphosphane iridium. Next scenario is if we have pi complexes. Hapticity describes the connectivity of contiguous atoms or adjacent atoms in a single ligand that are simultaneously and directly bonded to a central metal atom. So the superscript following the eta symbol denotes the exact number of atoms interacting with the metal. So for example, if a cyclopentadienyl ring has an attached ethene and only the alkene's 2 carbon atoms coordinate to the metal, it's named as eta-2-ethene. So as we can see in the example. But if the cyclopentadienyl ring itself is fully bound while it has vinyl substituent and it is not bounded to the metal, it will be named as eta-5-cyclopentadienyl ligand. So here are other examples. So cyclopentadienyl is directly bonded through 1 carbon. So we will not place eta here. And through the pi system of ethene, it is bonded to the metal. So we use eta-2-ethene. So the whole name will be cyclopenta 2,4-dien 1-yl Kappa C1 eta-2-ethene. Next, all 5 carbon atoms here are bonded. So for the cyclopentadienyl ring, we will use eta-5-cyclopentadienyl. And it's followed by eta-2-ethene since both carbon atoms in the pi bond are bonded to the metal. And last example, in here, eta-5-cyclopentadienyl vinyl, since we have vinyl group and it's attached to 1 carbon atom, so we will not use the eta convention. However, for the cyclopentadienyl ring, since all 5 atoms are involved, we will use eta-5. Let's apply the eta convention to the following organometallic compounds. So first, for this osmium complex, we have formaldehyde coordinated through both the carbon and oxygen atoms simultaneously. So it will be named as eta-2 formaldehyde. And aside from the formaldehyde, we have 2 of the triphenylphosphine and 2 carbonyl groups. So the name of the complex will be dicarbonyl eta-2 formaldehyde bis triphenylphosphine osmium. Next, we have this mixed haptocomplex. So the cyclopentadienyl ring is fully delocalized and it contributes 5 atoms. So we have eta-5-cyclopentadienyl. However, for the cyclooctatetraene ring, as we can see, it is not fully coordinated to the metal center. Only 4 of its contiguous atoms, or the 2 alkene present, alkene double bonds, are interacting with the metal center. So instead of writing the superscript, we will place the locants of the carbon atoms involved in bonding. So the name will be 1256 eta cyclooctatetraene. So that's the ligand in the bottom. And for the top, that's eta-5-cyclopentadienyl molybdenum. Lastly, for our final case, we will cover compounds containing direct metal-metal bonds. So the presence of the bond is denoted by enclosing the italicized element symbols of the metals within parentheses, and it's separated by an M dash, and it is placed at the end of the name. So to determine which metal is named first, if you have a heterometallic cluster, we follow the element sequence path shown in IUPAC Table 6. We trace the arrows, and the metal encountered last in the table sequence will take priority, and it will be cited first in the name. So for example, if we have a complex with rhenium and osmium as metal centers, since rhenium is listed last in the table, starting from here, so if you trace these elements, rhenium is listed last in the table, and it will be the priority in naming. So the bond will be rhenium M-osmium. Next, if we have multiple metal bonds, metal-metal bonds, we will write the total number before the first symbol. So for example, you have two osmium bonds that will be listed as 2-os M-os. And note, in nomenclature, no structural distinction is made between different metal-metal bond orders. So if you have a single, double, or triple bonds, it will be indicated the same way. Let's consider these examples. So as we can see, based on our discussions, we can see some organometallic compounds that have bridging ligands, they have pi ligands, and they have metal-metal bonds simultaneously in the structure. So you should remember all of the notations that we have discussed earlier. So going back to this example, for this osmium complex, it is bridged by an ethane 1,2-diol chain. So naming that will be mu ethane 1,2-diol. And each osmium, it has 4 terminal carbonyls, and because the two metal centers are symmetrical, we can name it as bis osmium, bis tetracarbonyl osmium. Okay, so the final name will be mu ethane 1,2-diol, that's our bridging ligand, bis tetracarbonyl osmium, and lastly, we append the italicized osmium M-osmium at the end to explicitly state that there is osmium-osmium single bond. Next example, the tungsten-rhenium complex, it has 2 bridging carbonyls, so that's di-mu carbonyl if we name it, and then 1 terminal carbonyl on rhenium, as well as you have 1 cyclopentadienyl on rhenium. Next, for tungsten, we have 2 cyclopentadienyl rings. And following the table 6 in the red book, tungsten is listed after rhenium, so tungsten is named first. We also place labeling 1 and 2 to the metals to indicate where the ligands are attached. So the complete name will be di-mu carbonyl, so this is our 2 carbonyl bridging ligands, followed by carbonyl kappa 2 kappa C. So 2 here is to indicate that it is bonded to rhenium, and then kappa C to indicate that the metal is bonded to the carbon atom, followed by bis 1,8,5 cyclopentadienyl. So 1 here indicates that it's bonded to the tungsten atom, followed by 2,8,5 cyclopentadienyl, since this 1 cyclopentadienyl ring is bonded to rhenium, followed by tungsten, rhenium, and lastly we have WM-rhenium to indicate that you have 1 tungsten rhenium single bond. Okay, so that ends our discussion on naming organometallic compounds. So see you on the next video.